So I am going to talk about two more things that we can, observables we can examine in our calculations. So MDPL, which is the molecular dynamics photoluminescence, and photoluminescence quantum yield. So we're going to start with MDPL. So if we, with your spin orbit calculation, there is a code that is in the bin on NERSC, which is modified from coding off human. So it's this OS underscore PL underscore scripts. You're also going to need from your coupling calculations all the OS underscore strength underscore VC dot XXX files. So these are your files that show the oscillator strength along the trajectory, and specifically the ones along for interband. So if we open up this OS underscore PL script, you're going to see what we have over here. And if you look in the red box, I have the values. These are the values of X in the oscillator strength files that you have. So however many you have, you should fill in here. Depending on what V script you use, you may also have to change this 4 in the %04G to 3, because that's setting it out to be 4 digits. And I think I'm the only one that uses code that sets it to 4 digits. So what this code does is it generates an oscillator strength file with just the homolumal transition through all of along your molecular dynamics trajectory. So to actually generate this spectra, once you have that oscillator strength file that was generated by the script in the last slide, you treat it just like how we treat absorption spectra. So you will plot it and you will get out a plot, which I did not include. I can probably add one quick.
Yeah, let's do it. The same style as Adam. So I will cancel the session.
So if you look at this, this is the MDPL for a few of my structures that I used on my Sanibel poster. So if we look at them, part of the reason we're interested in this is it allows us to calculate the width of these so we can compare them to experimental spectra. So then moving on to the photoluminescence quantum yield, we have a MATLAB script that I wrote to calculate the photoluminescence quantum yield for spin orbit coupling. I wrote this based on some Excel sheets that Aaron sent me. So you need the energy pop, 4-master optics, and the RRR file. And then if you run this, it will calculate the PLQY based on the Redfield tensor and the Einstein coefficient of spontaneous emission. The major thing you would have to change probably these first 3. Realistically, the 2 G's are going to be the same, but if you had a system that would require changing them, you would change it here. So this outputs these photoluminescent quantum yield values. So for this code, we use the average value for the near degenerate band gap transitions as our photoluminescence quantum yield, which is why we have 4 values here and then a final value. So we calculated for homo to LUMO plus 1, homo minus 1 to LUMO, homo minus 1 to LUMO plus 1. and then take the average of that value. And that's the end of my presentation.
Okay, please join me in thank you. Any questions in the room? What did you find in the difference?
So you need to examine if there's any degenerate states in your file. So due to the spin orbit, we basically end up with two degenerate states.
So what that file would just look like you have repeated lines?
What do you mean?
Or like, you said you can look at the file, it's also like degenerate, like would you just see?
Do you insert degeneracy manually or it automatically assess if any energy level is close enough?
We can insert it, it's a variable we insert. So it's based on the value of energy and whether they're the same or pretty much the same. So all my values are less than a milli electron volt difference. Or some of them significantly less than a milli electron volts.
If one needs to compute photoluminescence not by MDPL but by graphical approach, same as Sarah, Kia, Amara, are there any changes to the code, or you just modify the input parameters and use the same code?
What do you mean?
If you need to not keep bits, but if you just need the photoluminescence, which you are not showing in this talk, not a quantum view.
Oh, like the blue figures?
Yes. Does the way to compute blue figures similar but different from situation with single nodes?
Virtually identical.
Therefore, you skip it.
Yeah, basically.
Okay.
This is just from one of the other figures. It's it's virtually identical.
Okay. Yeah. Thank you. Okay. Let's check. Let's check if anyone has some questions in the chat line. And Adam, please look at this question and think how you would answer it.
Aaron asks, is MDPL able to capture Frank-Condon factors vibrational progressions?
It is a provocative question.
I hope so.
Let's give chance to Adam. Adam, would you like to just share your opinion to address this question? I know it's a little too steep step to listen for new methods 4 minutes ago and now assess it and compare. But just your vision, how would this MDPL method do anything comparable to Frank-Condon progression or very far, or do you see any connections? You see nothing, you can criticize that it is partial, just
yeah, I kind of can. I don't know exactly how to put it, but you have, the energy.
So what's the main condition to develop Frank-Condon progression? And maybe you can even briefly remind it to those of us who want such a refresher. Like, how does one come to Frank-Condon progression? Which conditions to nuclear degrees of freedom are imposed?
Vibrational states.
So vibrational, which means vibrations, interatomic distances, are they just point charges or something more than that?
I mean, there's something more than that.
Like you already answered. Sorry for making it as a little looking like exam, but you once answered one needs vibrational state. So instead of continuous exploration of different points on the potential energy surface, you are speaking of vibrational state.
Yeah.
So,
Like of the, of the entire molecule, or of portions.
So vibrational motion should be classical or quantum in order to speak about from quantum factors.
Probably quantum.
Perfect. Yeah. Thank you. And what do you think about? Do not hesitate to be critical. What do you think about the MDPL method that David has presented? Does it have any quantization of positions of ions?
Not that I can see, no.
Like when we run molecular dynamics in computational chemistry software, do you have strict exact position of ions, or they all atoms are like cloud which is smeared over the whole space?
I believe they're clouds that just just gives them electronic structure, bases their motion on it.
Okay, thank you. David, would you like to continue the discussion and summarize? You have all information, and I have no doubts. You know that. Only a little exercise to verbalize things.
So I think that's most of the reason we were doing MDPL, wasn't it? Because we need to worry about it over the trajectory instead of just at a random fixed point that we picked or get picked.
Yes. So right now we are approaching to the real life and potential interaction with reviewers of works that we do. So David is presenting situation from a constructive point of view, achieving good result. So in order to see how atomistic motion affects line width, this method is introduced. But if reviewers are trained to find any weaknesses, they will immediately tell any discussion of quantum factors is based on quantization of nuclear motion. If your nuclear motion is not quantized, it is not from quantum factor. And it will look like we are seeing it stupid and they are right. So one needs to find what Aaron invites us to do is to find. He gives us a task to find a bridge, to find a connection, to say that on one hand we appreciate and that if nuclear diffusion freedom are quantized, there is a progression that contributes to width of a line. On another hand, we can approximately get the same effect by scanning through whole amplitude of interatomic motions. Is it something what you wanted to say?
Yeah.
Aaron, would you like to summarize in a better way? Did we perform a good try answering your question, and how will you answer yourself?
I guess I would hedge and say it captures some aspects that you would see with Frank Condon.
Okay.
And that we're dealing with solids and high temperatures, so it's experimentally those wouldn't be resolvable anyway, unless you were doing very specific types of or very specific experiments, like low temperature or something. So it could be like a homogeneous line width.
Mhm. Many thanks, many thanks. So let me illustrate this discussion, and I think Adam will agree and appreciate it. So the rank content progression which Adam did compute in his fourth term shows that either charge transfer or optical transitions do depend on energy offset and have a progression of peaks when vibrational levels come of the initial and final state come into literal resonance. Adam, would you confirm that this figure looks similar to what you did in the past?
Yeah, it does. It looks like one of the figures.
Okay, thank you. And if one increases temperature, then through several mechanisms, the width of each individual peak will become broader, and several peaks originating from quantized nature of nuclear motion will start overlapping. So as temperature will increase, the system is coming to like quasi-classical regime, and the modeling of transitions with an account of this variety of transitions through classical mechanism will coincide better and better with quantum approach through Frank quantum progression. Aaron, would you take it as an improvement on our side?
I mean, I would buy it.
Okay, thank you. David, what do you think about another comment from Aaron?
Another aspect that is needed for Frank quantum is excited state potential energy surface. Here is only ground state. I would agree on both points.
Okay. So, any additional questions to David from the audience, from online audience, or from the chat line?